All right, scientists, in this video, I'm going to show you how to use a scatter plot graph with a line of best fit to predict the value of dependent variables for values of the independent variable that you didn't measure. Okay, and this is the graph we're going to use. This shows the relationship between the independent or x variable spring stretch and the dependent or y variable force. All right, and this is a set of data collected by a student in class that I graphed. Shows the line of best fit going as close as we can get it to the points we measured for spring A and the points we measured for spring B. To better understand how to do this, we're going to zoom in a little bit. We're going to focus just on the spring A graph. And we're going to get even closer. Just look at the first half of the graph so we can really see what's going on. Okay, here we go. Now, we learned in class that the line of best fit models or is the best approximation of the relationship between the two variables that we graphed. So the points we put on the graph led us to the line. The line is what's important. The line is what we're going to use to find the values we want. Okay? Now, we did not measure these three values of stretch to find the forces necessary to get that stretch in the spring. 2 centimeters, 7 centimeters, or 12. Okay? And I'm going to use these as an example to show you how to use the graph to get forces that would be required to get those stretches. Okay, so let's start with 2. Step 1, you're going to go on the x-axis to find the value of the independent variable you want to find the value of the dependent variable for. So that's 2. All you're going to do then is trace up on your graph from 2 to the line of best fit. And you're going to go over from the line of best fit to the y-axis. Okay, straight across from the line to the y-axis. When you get to the y-axis, you're at the point where you find the value for force in this case, the dependent variable that you're interested in. So if we go up from 2 to the line, over from 2 to the y-axis, we see that to get a stretch of 2 centimeters is going to require about 0.25 newtons of force. Now this is an approximation, okay? It's not directly written on the graph, but you can see that that line hits the y-axis about halfway between 0 and 0.5, and halfway between 0 and 0.5 is 0.25. So that's how much force you need to get that stretch according to this model of the relationship. All right, same thing is true for the 7 centimeter stretch. Find 7 on the x, go up to the line, go left over to the y-axis. Where you hit the y-axis, that's the force you want. Okay, and in this case, again, we're right in between 0.5 and 1. Halfway between 0.5 and 1 is about 0.75 newtons. And for our final prediction, find 12 on the x, go straight up to the line, left to the y-axis, and you see that that hits the y-axis between 1 and 1.5 or 1.25 newtons. All right, so our graph tells us that to get stretches of 2, 7, and 12 centimeters, we're going to need forces of 0.25, 0.75, and 1.25 newtons. Okay, now in your assignment, you're going to have to record these predicted forces in your table. So in the predicted force column for 2, 7, and 12, you'd write 0.25, 0.75, and 1.25. Okay? And then what you're really looking for is a pattern here. How is that force changing each time? So we see between 2 and 7 centimeters, the force required goes up by about 0.5 newtons. What we want to see is if that's a consistent change. Every time we're going up by 5 centimeters of stretch, how much force is required. Okay? All right, scientists, hope that helps.